Okay, so title of this talk is Uncertainty Relations in Pre and Post Selected Systems. Before I go to this, what is pre and post selected systems, we have to understand what is uncertainty. And we will see that this uncertainty relations in pre and post selected systems has two strange features, which is in fully contrast with Robertson-Heisenberg uncertainty relations. We will see that. Okay, so I will start with classical uncertainty. So let x be a classical random variable. It has more than one outcomes, which are denoted by x1, x2 and dot 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 xn. Then the standard deviation of the random variable x, or the outcome of this set x1 to xn, is defined as this way. This sigma x square is the variance. This way it is defined, and where this x bar is defined, this, which is the average value of this outcomes. Okay. Now, what is the significance of SD? It quantifies the variation or dispersion in a set of values. If the SD is high, the values are widely spread from the mean, and if it is low, the values are close to the mean. Okay, now this configuration can be understood from information dispersion perspective also. So we denote x1, x2, dot 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 xn as n number of different directions. Then we say that the information of x has dispersed along all these directions. If only one outcome occurs, then the information dispersion along rest of these are 0, and we will say that there is no information dispersion along different directions. Okay. Now, what is the quantum analog of this idea? So, in quantum mechanics, so we first have to prepare this system in a particular state. This is the bracket notation. So, ket psi is the initial state of the system, and this A is the observable, that is a Hermitian operator acting on a Hilbert space, and let these outcomes, these are the outcomes of this observable after measuring. So, these outcomes are nothing but the eigenvalue of this observable A, and its corresponding eigenstates are the ket A, ket 2 and so on. So, post measurement state of the system will be these eigenstates. Okay. And similarly, the standard deviation of this observable A is defined like this. This is the variance this way, and it has a compact expression in quantum system with this initial state and observable like this. Okay. Now, the similar again, so we can say that this information of A has dispersed along all these eigenvalues, right? Similar to this situation, this one. Okay. Now, this similar thing can be understood from another perspective, an equivalent way. So, prepare the system in state ket psi, measure the observable, and then okay. So, first the standard deviation can be written in this way as well, right? So, sum over these quantities. So, we call these quantities as information carrier of A, and how to interpret this summation kind of thing. So, this thing can be understood like make a direction along this psi and psi orthogonals. So, these psi and psi orthogonals, all of them form a basis such that this identity can be written like this. Okay. Now, okay, yeah. So, these things are the information carrier along, for example, this average value is the information carrier of A along psi, and these quantities are information carrier of A along this all these orthogonal directions. Okay. Now, okay, so this is the information theoretic interpretation of the standard deviation, and now let us move on to this geometric interpretation. So, Aharonov-Weidman identity says that we can write this vector, unnormalized vector, like this. Okay, so the interpretation of this equation is that the action of A on psi has two components. One is along psi itself, and another one is the orthogonal state to this psi. Now, this orthogonal state is unique; it is not arbitrary. To have a visualization of this equation in 2D, so let this vector is represented by A psi, and this is the psi vector. Then this should be this orthogonal to this psi. This one is the orthogonal, psi perpendicular. Okay. Okay. So interpretation is that the action of A on psi actually disturb the state psi by this much amount. By calculating this much amount, it will say that how much your initial state has disturbed due to the action of A. Okay, and this is the average value of A. Okay. Now now let us actually take different configuration by replacing psi by phi. So here the preparation remains same, psi, measure the observable, and then instead of here you had earlier psi, now we want to replace it by phi, a different state, and it's all those orthogonal states such that these states form a basis, orthonormal basis, and the identity is written like this. Okay. Now in this case also, of course, we will take all the information carrier, this one. If you remember earlier, instead of psi it was phi, right? Instead of phi I perpendicular, it was psi I perpendicular. So of course we will take the sum over all these information carriers, and again we will say that in this configuration the information of A has dispersed along this phi 1 perpendicular and so on. So we will take as a information dispersion measure like the sum over all these perpendicular direction, summation of all this information carrier along all this perpendicular direction to this phi. Okay. Now this similar thing can be this thing can be replaced by weak values, because weak values exist in quantum system, and okay, the similar thing can be understood like this. So we can replace that thing by this weak values. Weak values is defined like this. Okay. Now the question is, this is an arbitrary replacement of this psi to phi, right? So is there any physical connection to this thing? So I would say that yes. Now what is this weak values? What are these? So we'll actually it exists in experiment, so we can okay. So how to get it? So first prepare this system and an ancilla, and evolve both of them under unitary. Here the operator of interest is here, and take this interaction coefficient Gt to be much less than 1, and then project the system along this phi. So and your ancilla will immediately collapse to this state, and approximately, because we are taking this Gt to be much less than 1, and this quantity is the weak value, it exists here. Now how to get this weak value? So it can be shown that if you calculate the x and p position and momentum variable of the ancilla, then we will get the real part of the weak value and the imaginary part of the weak value. That's how you get the full information of your weak values, right? Okay. Now this this configuration actually had some meaning, right, in terms of weak values. Okay. Now the weak value, So this is our pre-selection and this is our post-selection. So that was the first title of our talk, the pre and post-selected system. Okay. Yes. So this is the compact form of uncertainty of an observable in pre and post-selected system. So this is our main result of our work. So this is our quantity of interest. And if you replace this phi by psi, you will get back to this original standard deviation in standard quantum system. Okay. Now so this was the information theoretic interpretation or information dispersion interpretation. Now the geometric interpretation is this, that the action of A on psi has two components. One is this and another on the quantity of interest, standard deviation in PPS system. Okay. Now a parallel comparison is that standard deviation has a standard system has a standard deviation expression like this, and PPS system has this. Okay, the carrier are this, and in PPS system the carrier are this. Okay, and geometric interpretation is something like this. Okay. Now, in standard system, the uncertainty relation is represented by this inequality, which says that standard deviation in a standard quantum system is restricted. Actually, their standard deviations are restricted by this much amount. That means you cannot, the product cannot go beyond this quantity, and this right hand side highly depend on this non-commutativity. Actually, non-commutativity is very important for standard systems, and its tighter version can be shown to be this. Yeah, and we have shown that uncertainty relations in standard. It should be PPS system actually. Yeah, so in PPS system, the uncertainty relation is this one. So this is also our main result. So as you can see that the same commutator term is there, but there is an extra term. So this is of course due to this post-selecting the system, and analog to this uncertainty, tighter uncertainty, this one is this. And what is this WAB? WAB is nothing but this one. So again, if you put this phi to psi, then this WAB will be nothing but the product of the average values of A and B, and this imaginary part will be 0, and we will get back to this standard uncertainty relation. Yeah, okay. And interpretation is obvious that the product of uncertainty of two incompatible observable in a PPS system cannot go beyond this quantity. Now, two interesting feature in PPS system which cannot be seen in standard quantum system is that this non-commutativity matters in standard systems, right? So if A and B are commuting, then this lower bound will be like 0, right, achievable. But in PPS system, it can be seen that even if A and B, the commutator of A and B are 0, this right hand side might not be 0, right? Even if this is 0, this might not be 0. And if this quantity goes to 0, then there is another term, this tighter version, right? So it shows that non-commutativity actually doesn't matter in PPS system, but in a standard system it matters. So this is the first strange feature, and the second one says that what is impossible in a standard quantum system is possible in PPS system, in the sense that in standard quantum system, if A and B are non-commuting, then it is impossible to have both standard deviations of incompatible observables A and B are 0. It is impossible to have both of them 0. That means you cannot prepare a initial state psi for which both of them 0. So this is the sharp impossibility of sharp preparation of initial state in a standard quantum system. But in PPS system, we have shown that even if A and B are non-commuting, we can have both the standard deviation of incompatible observables A and B 0, provided this condition is satisfied. That means if we take both, we take the post-selection to be satisfying this condition, then we can have both the standard deviations. Yeah. So this is the this is the comparison you can see.